decision trees and random forest. So as part of your analytics module, as your y, that is your dependent variable, becomes multinomial, wherein it has more than two options, when it is a categorical variable, it becomes difficult to do modeling using traditional algorithms like logistic regression. That's where decision trees are very handy. So we'll try to understand what we're going to cover first, and then we'll just step into the world of decision trees and random forest. So in this session, we'll be learning more about decision trees. We'll cover some examples theoretically, the principles which are used when you're doing a decision tree, which includes entropy, information gain, evaluations, demo, and then a brief about random forest. So the problem at hand is that you have a large amount of historical data and you need an algorithm for a future data outcome. That is, you want to either classify or predict. So suppose you have data like previous games played, right? And then you have something like a black box, which is a learner, which has to do a classifier's job, or if it is a point prediction, which has to do a predictor's role. So based on the future games, you want to classify what would be the outcomes, right? So say for example, nothing different than what you had done in logistic regression, wherein you had used historic data to relate the y's and the x's, and then punch in some values of futuristic x's and accordingly get the outcome for the futuristic y. That is what the whole problem is about. It's a classification or a prediction problem. Now, why do we use decision trees? First of all, for simple representation, so that it's easy for anybody to understand. When you went through the logistic regression models and the linear regression models, one thing was very clear, that you need to have a strong base in statistics. There is a lot of mathematical computations, there is statistical significance tests and all those things. We want to avoid some of these things which becomes difficult to understand for a business perspective, right? And that is why we want simple representation, graphical representations also. So the framework of business rules that can be used going forward. So for example, when I learn from data, I create an equation, it becomes difficult to interpret by a business guy. But the same if represented by ways of a decision tree, it becomes very easy for a person to understand. So basically, ease of explanation to business, ease of understanding for the business, that is also one important perspective. Now also what is important over here is its flexibility to modification. Right? So it becomes very easy to modify a decision tree based on your practical usage. So if it is a prediction model, you might want the decision tree to be very complex, but if it is a depiction model, that means if you want to just show it for visualization, then maybe you can chop off basis some parameter optimization so that you can fit it in PPT or something like that, so that it becomes easy to plug it into a PPT. It's only the multivariate algorithm which it becomes very easy to depict over here. So when my y has more than two classes, that it's not binary but more than two, that is where decision tree becomes mandatory in a way. And it can be applied to categorical as well as continuous target variables. So all you need to do is just a little bit of tweak, and it basically understands that yes, I have to do a prediction or a classification model. And these are the major reasons as to why decision trees are used. So what are the key requirements? One, attribute value description. So the object or case must be expressed in terms of fixed collection of properties or attributes. Hot, mild, cold, these are just classes levels in the data. So basically what we're talking about is that your y should have attributes or classes within them, right? And obviously this should be somewhere tagged in the data. So if your data doesn't have a y, you wouldn't be able to use it. Then there would be a predefined classes, that is target variables. Target function has discrete output values, which could be boolean, that is 0 1, or it could be multi-class like true, false, don't know, right? Say credit, in case of credit it could be default, no default, or it could be something which is in between, right? So you can do that also. Obviously when you're doing decision trees, you need large amount of data as compared to logistic regression models and linear regression models, which comparatively can work good in a smaller set of data also. Reason being that decision trees come with one problem, a problem called as variance, which comes because of the bias and the variance trade-off rules, right? So it's something like this. So if you're looking at a shirt which you want to get for yourself, right? So you have two options: either you go to a custom fit or you go for a ready to wear apparel store. Now a custom fit is something like decision tree, right? And a ready to wear is something like a logistic regression model, right? Wherein in a ready to wear, what is considered is just your shoulder blade length, right? The chest size, so very few variables, so the model is not complicated, right? And it's looking at the overall thing. Whereas if you go for a custom fit shirt, it would look at most of the attributes like sleeve length, your arms width, everything, your chest size, even the torso length and all those things. So maybe instead of 2, you're considering 7 or 8 attributes, right? So it becomes a complex model, and that is what decision tree is trying to do. It is trying to overfit on the data. Obviously, as per se the bias, it's very high in terms of logistic regression model, but when it comes to decision tree, the bias is low, so it tries to make everybody happy, right? But now in this case, if you try to give the shirt to your brother, right, who is almost the same size as you, he might feel it is uncomfortable because somewhere on one of the parameters it's not fitting well. As compared to that, even if you give your shirt to your dad, maybe he might not feel that uncomfortable, right? So that's about how the bias variance trade-off is playing, right? So a decision tree basically reduces the bias but increases the variance, so prediction goes wrong. And the same thing happens when you're trying to give your shirt which is custom fit to your father. So what happens is that it fits very good on you, but as the data changes, so that becomes your father, it is not giving a comfort fit. On the other hand, if you're looking at logistic regression models, they are something like ready to wear shirt, which are very simple models and which are not overfitting on the data. And if you try to use it for somebody else also who is looking almost of the same height and width or dimensions as you, it will fit that person reasonably. And that is why you can see that a 40 size shirt fits a person who is 39 as well as a person who has a 41 chest also. So that is about the bias variance trade-off. You need to relate with this so that you understand these concepts. From the definition perspective, a decision tree is basically a classifier or a predictor in the form of a tree structure, right? Now again, you can look at it from the leaf branch perspective, or else you can see from the root perspective also. So just imagine that you are having a look at something like a coconut tree versus a banyan tree, right? So again, within decision tree there are many different methods. So there could be something which is called as cart, which is called as classification and regression tree, and there could be something which is called as shade, which is somewhere more statistical. So a shade tree basically is an acronym for a chi-square automated interaction detector tree, which is basically good for profiling, and it's something closer to a banyan tree, wherein the branching happens non-binary. That means from one node you can have more than 3 branching also, whereas in a traditional tree it's a binary tree, so from one node you can see only 2 leaf or 2 arcs going out. So that's the difference. And obviously the decision tree which we are talking about right now is more related to CART, that is classification and regression tree, which does binary classification and not non-binary classification. So the branching happens in a binary, so it can only give 2 branches at one time from a node. So key parameters over here would be the decision node, that is specifies a test on a single attribute. Leaf node indicates the value of the target attribute. Arc edge is the split of one attribute, and path is a disjunction of the test to be made for the final decision. So decision tree classifies the instances or examples by starting at the root of the tree and moving through it until the leaf node. So let's just look at the illustration which is shown over here. So with some data related to offense, right? So it's talking about the start node, right? So which to start? Root. Where should the root be? Which node to proceed? That is shown on the 2. And the 3 is when to stop or come to a conclusion, right? So your categorical Y over here is a decision which is talking about whether you lost or won, right? So in this case it has just have 2 options, right? And when you are looking at data, now you can represent this in this way. So the overall data starts at the starting node, right? So wherein it is mentioned the 1, this is where the data is completely present. So supposingly you have 10,000 observations, this is where you start. Then when based on a variable which you find as significant to partition the data, you start partitioning it into yes versus no. That's where it starts getting partition. So if you had 10,000, if the outcome for fired starts was yes, no, and say 60% of that was a yes and 70% or 40% would have been a no, that is where the partition happens. So based on a condition, it goes to a yes branch and no branch, right? And the true is on the left hand side and the false is on the right hand side, and then again the data gets partitioned into small blocks. You can give conditions as to when the node branching should stop. So if a node doesn't have observation more than 500, you can give that as a condition that stop the branching over here. So all these parameters can be controlled. So a random split, the tree can grow huge, right? But obviously you are seeing that there is only binary partitioning. You don't see at any of these partitions that it is going more than 2 branches, right? So the tree is hard to understand. These trees are hard to understand. As the tree becomes large, it becomes difficult to infer, right? So you can give some conditions to control that. That is called as pruning of a tree. So in this case, a training data set is shown. Now, as compared to a linear or logistic regression model or traditional modeling approach, wherein the training data set is usually 70 or 60% of the overall data, and the testing is keeping the other part of the data. In decision trees, you typically try to keep the training data set small as compared to what you would do in traditional models. This is a way to work around with the bias variance trade-off. So you can have a look at this data which is shown. There is an outlook variable, there is temperature, humidity, windy, and there is class. It's basically trying to understand that given these conditions, that is the weather outlook, whether it is sunny, overcast, or rainy, the temperature ranging between these values, the humidity as so, and the wind conditions as so, was the match played or what the tournament held. So there are these couple of flags which have been flagged. So based on historic data, these flags have been created, whether the match was played or not played, right? And in future, if the values of outlook has these values, given the temperature is so, the humidity is so, and the wind would be so, would we be playing a match? That is what is expected. So that's a decision tree, right? So let's have a look at the next slide. So numerical attributes like temperature, humidity, categorical attributes, and outlook, that is windy or sunny, these are categorical attributes. The class of the data which you want to model on is play versus no play. So you're seeing this tree over here. So the outlook is sunny, overcast, rainy. The overcast is mentioning humidity, windy, and you can see a bifurcation over there again, play, no play, play, no play in the end, which is actually a decision, right? So based on all these values, you would be creating a decision tree, and obviously you are not going to do that mechanically. You will be using some program in R or SAS or SPSS to do this. Obviously we will be doing that in R. So the leaf node each represents a rule, right? So you can see that from the screen. Okay, so there's again this example. So how to read this, right? So if you go just reverse integrate, it says if it is a sunny day and humidity is not above 75, then you play. If it is sunny day and humidity is above 75, then you do not play. So that's how you just read the rules, right? But again, with some change in the data, the rules can change, right? So you cannot always say that these rules will hold on for a very long time, and that surely is a problem with decision trees. So you have to make sure that the data keeps on updated in your algorithm. So is it the best classification? You will have to actually test that. You cannot directly say that, right? So whether this is really working in your favor or not, the accuracy of the classifier is determined by the percentage of the test data set that is correctly classified. And surely you can say that it would be more correct to do the test on the not on the training data set, because that is where you have created the model. So as we said that decision trees overfit on the data. So when you do the test on the training data, it would be very good. But when you change the data, you will see that it starts giving weird results. So for example, if you look at the performance of cricket or players in India, right, wherein conditions are conducive to their requirement, it's a slow pitch, it's not a fast pitch, it's a turning pitch, so our bowlers would outperform over here. But maybe when they go outside, wherein the pitches are flat, it's a fast pitch, they might not perform that great, right? And similarly for the batsmen. So you will have to make sure that the accuracy is tested in a test condition and not in the training data set, which is specifically good for them. So you are again seeing this test data, which is again a small slice of the same previous data. So when you're doing this for the first time, you would be just chopping off your data into a training and a testing data set. And obviously you'll create the model on the training and you'll apply it on the testing data, right? And you'll do the prediction and you'll check really what is the classification. So the class should actually be flagged in the data, and then you will be checking the class per se your definition which is coming out of the model, and then you will check the accuracy rate. This again goes back to the same definition of type 1 versus type 2 error, right? So, and again, this is a misclassification or something which is called as a confusion matrix, wherein you expect the true classifications to be correct and the false classification to be low, right? So rule 1, two records sunny and humidity less than or equal to 75, that is followed, then one is correctly classified, the accuracy is 50%. The rule 2, that is sunny and humidity is greater than 75, the accuracy is 50%. If you follow the rule 3 of overcast, then the accuracy is 66%. So obviously you will have to use that. The principled criterion: select an attribute to test at each node, choose the most useful attribute for classifying examples, right? But obviously it will be a combination of attributes and not just one single attribute. Now there are again some things which you have to bear in mind. So what are you going to look at? Is it the information gain or the loss criterion? So what is the information gain? It measures how well a given attribute separates the training examples according to the target classification. So basically how well is the partitioning happening. This measure is used to select among the candidate attributes at each step while growing the tree, right? So you might use a Gini coefficient, or you might use an information gain or anything like that. That depends upon what you want to use. All of these parameters can be tuned and selected when you're running the algorithm. So entropy is a measure of homogeneity of the set of examples. So given a set S of positive and negative examples of some target concept, a two-class problem, that means that the Y has two class data, a yes or a no, true or a false. The entropy of the set S related to this binary classification is entropy of capital S is equal to minus P, that is the probability of the P, log to the base 2 P probability of P minus P, and in that you have N, that is number of observations, log to the natural base 2 P and N, that's probability of N, right? So you're basically trying to check the positive versus negative, right? So the P is the positive case and the N is the negative case, right? So you'll be doing a negative probability of positive case log to the base 2 P probability of the positive cases minus P to the negative cases into log of 2. Log 2 is nothing but the base 2 P, and it's the negative case. So this is coming out of as an entropy. So at every node this entropy would be computed, and that would be used as a definition for further partitioning of the data. And suppose S has 25 examples, 15 positive and 10 negative, so say 15 plus and 10 minus cases. Then the entropy of S related to this classification is entropy of S in outside bracket. Now because you're doing the computation, you're taking this outside. So minus 15 by 25 log to the base 2, 15 by 25 minus 10 by 25, that is the negative cases, divide by 25 into log to the base 2, 10 by 25. This gives you the entropy for that specific one. Right. So the entropy is 0. Now this is from the fundamental understanding perspective. So if the entropy is 0, now when you're looking at the screen, you're getting an X versus a Y. So probability that X is equal to 1, and on the Y axis you have the function h of X, right, which is nothing but the entropy. So you're measuring it from 0 to 1 on that scale, and 0 to 1 on this scale as the probability of X being 1. So you're seeing a bell-shaped structure over here, right? So at 2 points, that is at the start 0 and at the end 1, right, when X is equal to 1, you're seeing that the entropy goes towards 0.5. So the entropy is maximum if we have no knowledge of the system, or any outcome is equally possible.